For our very last topic in this class, we're going to look at systems of equations. Now, systems of equations are something you've studied before, so we'll look at them from a new perspective, but let's begin by just refreshing what we do know from the past. So likely all of our experience so far with systems would involve systems of two equations with two unknowns. And even more specifically, they'd probably be linear equations. So I'd like to start by doing an example. It may feel very familiar to you, or maybe it's been a little while, but I think you've all probably seen them. So let's say, for example, that we had two equations. Let's say we know that x plus y is equal to 6. So you could rearrange that nicely to look like y equals mx plus b. So it's just a linear equation. And then our second one will be another linear equation. How about 3x minus 2y is equal to 8? And our techniques of solving from the past, just to also bring those in, would be typically called substitutions. And I'll demonstrate that one here. Elimination. We will also show elimination. And then graphing is a great way for sure to check, and it can be a nice way to solve when the solution involves integers for x and y. So let's just walk through these different techniques. By substitution, what it would mean is we need to take one equation, the first or the second, doesn't matter, and isolate a single variable. So in the system that I just gave us, it probably makes the most sense to grab the first equation and isolate x or y. Again, it doesn't matter. So how about I just isolate y by subtracting 6 from both sides. And then what this method does then is anytime we see a y in the second equation, we are going to substitute in that equivalent expression for y. So anytime I see a y, I'll be able to plug in negative x plus 6 in that second equation. So let's see, let's start writing down that second equation. 3x minus 2, leave some space to insert that new definition of y equals 8. So then again, we're just going to paste in that negative x plus 6, which is an equivalent representation for y. So this is what you guys would remember from the past as solving by substitution. What we've done in substituting is we've created a linear equation of one variable now, which we can solve for x. And if we can solve for x, then we can plug it back in to the substitution equation to arrive at a solution for y. So all I'm doing so far in this equation is distributing the negative 2 to the negative x plus 6. I'll collect like terms. And then again, since this is linear, all in terms of x, we just do our algebra dance. I'm going to add 12 to both sides, and then I'll go ahead and divide both sides by 5. So pretty easy to get to a solution of x equals 4. And then, as I mentioned, we're just going to sub that in to the equation from a moment ago, which was y equals negative x plus 6. That's probably the easiest place to go, and that will allow us to solve for y. So then we'll get y equals negative 4 plus 6, because x is 4, and it says negative x plus 6. So negative 4 plus 6 sounds like should be 2. Cool. So our final solution is often stated in problems like this as an ordered pair. So you would just say 4 comma 2. So that's what it looks like to solve by substitution. And hopefully that feels like a familiar technique. I'm sure there are some of us who said, yeah, that was the way I used to do it. That's actually my preferred technique. So substitution is a great technique for sure. Let's also show the same problem though using the elimination strategy, which is just a little bit different. So same example. I'll just write it down again so we can work it from the top. So that was x plus y equals to 6. And then it was 3x minus 2y is equal to 8. And now we're going to go at it by elimination. And the elimination strategy, just to contrast it with what we just did with substitution, means we want to be able to add the equations so that by adding, we eliminate one of the variables. In the system that I just wrote down, if we add right away, notice that neither x nor y will cancel, right? So that means it's not ready to eliminate yet. So often we simply multiply one or the other, or potentially both equations by a number to force one of the variables to eliminate. Let's break that down a little bit more. Let's say I leave the second equation in green alone. If I want to leave that one alone, then that means I have one of two options. I either need to multiply the top equation by 3, or how about even negative 3, so that this first term here would become a negative 3x, which would cancel with the term below it. Or I could multiply that red equation by 2, so that I get a positive 2y stacked above a negative 2y, and then again that would eliminate. So either route would work well. I'll go ahead and show timesing the red equation by 2. 2 sounds a little easier than negative 3. So when I multiply that whole first equation by 2, we get 2x plus 2y equals 12. So just make sure you're timesing the whole equation, not just the left side. And then at that point, like the name of this method implies, we are going to add and eliminate. So some people call it the addition method or the subtraction method. So when I add, I get 5x. The positive 2y and the negative 2y cancel. On the right side, 12 plus 8 makes 20. Dividing by 5, we get x equals 4, which should sound very much like what we found a moment ago in our other method. And then you can sub x equals 4 into either equation to find y. I'll just pick on the first one because that looks a little easier to me. So I'll plug in 4 for x and subtract that 4 from both sides to find y is 2. So our solution using this elimination strategy would be 4, 2, and I'll float back up to our substitution method and just show that we did in fact get the same solution. Cool. So you probably have a preference between the two. It's good to be familiar with both. And I did mention graphing, so I'm just going to pull in, I graphed it already, a graph of the system that we just solved those two methods. So you'll see again, the first equation I had given us was x plus y equals 6. That's showing here in red. And then the second equation was 3x minus 2y equals 8, showing in green. And we can find that the solution graphically is that ordered pair 4, 2. Oops, that just made it kind of hard to see. But again, the point is that when you're solving, there is a graphical understanding as well. So when you're solving a system of two linear equations, two unknowns, you're just finding where the lines intersect. So technically with straight lines, it's possible for them to never intersect if they're parallel. There's kind of a weird situation where they could intersect always, in which case there's infinitely many solutions, or your more typical approach is what we just saw here, where they hit just one time. So that's a reminder of methods from the past.